the recording before I forget. Okay, so in the last class, we basically finished reviewing number systems with special emphasis on Boolean or on binary, as you can imagine. Uh, in today's class, we'll talk about Boolean algebra in general. So, by the way, there will be more notes than necessary for you to eventually read at home. And feel free to review the textbook that we have for this course as well. And if you have any questions, always reach out to me and ask me during my office hours. So, Boolean algebra, a quick recap. George Boole was basically a logician who tried to describe logical decision-making process in terms of mathematics, right? And he came up with a new branch of mathematics per se called the Boolean algebra, where he had basically binary variables. But by binary, we don't necessarily mean the binary number system, something that has two values. And for his case, it was true and false. So something could either be true or false. And then about a century later, Shannon connected that Boolean algebra with hardware in a way that you could find hardware to represent the variables in Boolean algebra and apparently solve a hardware or design a hardware by simply doing math. Right? So that's how this revolution began. And as we discussed in the history section of this lecture, right? So now putting this together, true and false can be represented as 0 and 1 in binary. One other quick point is in Boolean algebra, we use different variables. We have different representations, A, B, C, D, you name it, doesn't matter. But irrespective of what these things are, they can only have two values, 0 and 1. So it's like comparatively simpler to handle, honestly. And we can describe any Boolean function using what's called a truth table, and we'll quickly review that truth table moving forward. All right. Okay. Before I show and talk about the truth tables, let me introduce you to. Again, this is just a quick review. That's why I'm just brushing up on this very quickly. Some very common Boolean operators and the foundational ones. These are and, or, and not. Apparently, if you have these three functionalities available in a hardware, you could implement any logic. That's the beauty of it. The simplicity is basically what makes it unique and so impactful. You just need to create, just imagine what I mean by that. If you just need to create three different hardware representations or circuits per se for AND operation, OR operation, and NOT operation, and you're basically done. You can take any decision. I mean, you see, just imagine that, how simple this approach could be. Yes, it may not be the most optimum to do it this way, but it will work at least, right? We'll talk about optimization and whatnot, but this is a quite fascinating stuff. That's why it has taken over the world, as you can imagine. Uh, Not, in other words, obviously, just to familiarize yourself, is often called inversion or complement or negation. So you get used to this term. We typically represent invert of something with a bar on top or just a prime. And in some cases, people also use tilde to represent it, but this is very rare. In most cases, we'll be using either this or that. For AND, we typically represent it with a dot, or sometimes people just don't even use dot, just put them side by side as a product, right? So it's kind of like what you learned in set theory in mathematics, intersection and union, remember? So so imagine you have one, anybody remembers Venn diagrams, right? So you have two sets, set A and B. This is the intersection of these two sets, right? Apparently, that's exactly what AND is. It's basically what is common between these two. And OR is similar to the union of variables in sets. And we represent that with a plus symbol. So when you're dealing with binary, don't misjudge this to be an addition operation per se. We have to just be mindful of, oh, this is a Boolean operation, not really an add. Am I making sense? So although it looks similar to an addition symbol, but it's basically an OR. And further down the line, you get used to something like this. This is a symbol for XOR or exclusive OR. We'll talk about it soon in this lecture. So just keep that in mind. This is OR and this is exclusive OR, XOR. Moving forward. Now, there is a concept called a Boolean function or operator being complete. I mean, it sounds very good. It's a complete function, complete set. What does it mean? It means that using a set, you can represent any random logic. If you get a set of Boolean operators that is capable of implementing any random logic that you can come up with, that is called a complete Boolean set. Okay, as the name suggests, as you can see. So the easiest way, as I just told you, if you have AND, OR, and NOT gates, by gates I mean circuits that represent these three operations, you can implement any random logic, as I just told you. But that's not the only option. There are other options, right? AND, OR, and NOT are easy to understand based on our daily logic. But there are other logic gates like NAND, for example. NAND is nothing but, say, not AND. Just take AND and invert the output. That's all. Flip the outputs. That's what NAND is. Okay, we'll take a look at the truth table as well very soon. But just keep that in mind. It's similar to AND, except for the fact that you also invert it. What is the uniqueness of NAND gates? So if you implement a NAND gate in hardware, that's the only building block you need. Just imagine it's a Lego that can help you shape anything you want. Wouldn't that be pretty unique Lego, right? So that's exactly what NAND is. NAND is a sole sufficient operator. It's pretty rare. There are only two, NAND and NOR. NOR is, as the name suggests, exactly invert of OR. Just take an OR gate, and if you invert the output, you get an OR gate. All right. So NAND and NOR are very useful, as you can imagine, because if you can somehow make a NAND gate out of it or NOR gate out of something, you can like project it to universality. Like any logic could be implemented. Now, there are other sets like this. These are not the only one. For example, apparently AND and NOT is also functionally complete. Is that a surprise for you? Can anybody tell me why it is not surprising? First, we start with, if you give me AND, OR, and NOT, I can do anything. Great. Then I say, okay, let's bargain a little bit. Let's not do OR. Just give me AND and invert. I can do anything. You see my point here? Well, you can always get more, but if you could do it less, that's even better. So instead of AND, OR, and NOT, I could just do it AND and NOT, OR and NOT. The reason is AND and NOT could be combined to make, anybody can guess? NAND. Yes, and OR and NOT could be combined to make NOR, because NOR is basically an invert of the OR. So if you take an OR gate, put an inverter after it, you get a NOR gate. And NOR and NAND are basically self-sufficient, as you can see, right? So that's why these sets are also complete sets. Obviously, when you're shooting for something, when you're shooting for a design, you're going to shoot for the most optimized design, which uses least component, as you can imagine, right? But there are reasons why people still want to use a mix. Remember, you can. Simply because you can doesn't mean you should. You can represent any Boolean function with NAND gates, only NAND gates, if you don't have any other gates. But it's not going to be the most optimized. And what do I mean by optimized? In terms of speed, in terms of area that is necessary, in terms of power demand, it's not going to be the most optimum design. It will work functionally, but it will not be the most optimum. But if you bring more gates to the mix, like NAND, NOR, invert, XOR, blah, 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 the more things you bring to the mix, the more optimization opportunities you will have. All right. Question. Yes, exactly. Yes. Thank you. I'm trying to stay very superficial here deliberately because I kind of assume that you have gone through some of these basics. If not, please let me know. I'm more than happy to go deeper into the why of this and more. And also, if you want to do a little bit thorough quick review, it's also available in the textbook, right? The one that has been recommended. But I'm more than happy to talk about it. And you're absolutely correct. The reason why you could represent or with N and not is basically you can use the Boolean logic and some theorems, which we'll see right here. Ready for it? It's very quick review again. And most of these are basically common sense. So we'll be using all of these simple steps quite repeatedly throughout the course to optimize the Boolean logic expression. Let me take a step back. What's the big deal of these logic expressions? Basically, in our daily world, we represent different real variables with different Boolean function. Okay, I gave you a very simple example of a car. I don't know, like a car alarm going off, right? If for some reason you don't have your seatbelt on, you don't have the right gear selected, you don't have these and that, maybe there will be a alarm going off, right? That alarm going on or off is the output function. It could either go like the alarm could either be on or off, so 1 or 0. So the output will be determined by multiple variables. Number one is the seatbelt on or off, so that's a variable A. Is your gear, are you in park mode or are you in the drive, right? So that's another variable for you to consider. And so many other variables could be put in there. So that's how you represent real life events in terms of a Boolean function. Notice that. So these Boolean functions are not just, we're not trying to do math for the sake of math here. We're representing real life situations in Boolean variables. And then those Boolean variables are put into Boolean algebra to solve. Because we are not going to manually make this logical decision that should I turn on the alarm, because a machine cannot think like us, right? It has to be logical, a chain. Okay, let's take a very quick tour through this. Notice, plus represents or, by the way. When you take x or 0, it's always x. Is that surprising to you? All right. Is any of this surprising to anybody? All of let me know. And no? Okay, by the way, to help you with that, let me take a step forward in here and show you what truth tables are. So I think if we take a look at 3 truth tables, and, or, and not, everything else could be calculated. Even if you don't want to use your logic to understand why this is so, you can always use simple calculations to check whether this is right or wrong. So and, as I told you, just take a look at the truth table for and. Your output can only be 1 when both variables are 1. And by the way, this is just 2 input version. There could be 3 input and. I shouldn't say both variables, I should say all variables. So if you have a 3 input and, the output will only be 1 when all 3 are 1. Or 4 input and, all 4 should be 1. So that's how we should talk about things. But apparently we always mostly show 2 input gates, because you can come up with 3 input gates with multiple 2 input gates. So this is like the building blocks essentially. All right. So that's very simple truth table. As you can see, every other combination will give you 0. Okay. Or interestingly, you only get 0 when both variables are 0. Any other combination will give you 1. Quite opposite to each other, right? Does that make sense? All right. Invert is basically whatever you put in as input, you get the output as opposite. All right. Now, using these truth tables, super simple truth table, we can go back and calculate any random one of this. Okay. Say, for example, let's do this without any loss of generality. X plus 1 equals 1. Okay. So x could either be 0 or 1, because these are binary variables, as you see. When you put x equals 0, you have 0 plus 1. Plus represents or. As I just showed you, or will always give you 1 as an output, except for the case where both operands are 0, right? So here, you at least have one of these operands non-zero. So the output will always be 1. Does that make sense, folks? Okay. And what if x was 1? Well, even better. You still get 1. So all you have to do is plug in the binary values. And there are just 2 options, as you see. Put in 0 and see how this looks like. Put in 1 and see how this looks like. Given the fact that you already know the truth table for or and AND, and invert. These three are kind of like the fundamental concepts. You agree upon this three truth table, and then everything else will fall in place. Are you all good? Okay, I don't want to bore you by going through all of this, but please take a please take a look at them, because we'll be using them quite often to simplify Boolean expression, and this will be part of your exams, your homework. So obviously, one thing that we like repeatedly use is AND of the same operator is basically itself. You can just keep doing this x, like no matter how many times you do it, it's always going to be just one. And similarly, OR of the same operator over and over again will always be the single operator. So these are repeatedly used to simplify Boolean logic functions. And you will see, hopefully today, if not today, then in the next class, how that translates to where, how does it impact the overall circuit design? By simplification of Boolean function directly leads to reducing circuit footprint, sizes of the circuit. Okay, all right. De Morgan's law is right there. This is probably one of the most important law. Besides, the other law is not here. I'll show you later. So apparently, all of these laws are used to simplify the Boolean logic functions. Did I skip something here? No. Okay, it's fine. So in this slide, we can do a little bit of practice together. We have just tried something similar, but let's do one more time, right? This is your AND function. And I'm asking you to try to create the truth table. And basically, this is AND and this is OR. And we have just discussed the truth table for AND and OR, right? Considering that we have these two in mind, can we come up with the truth table for a random function? Like, let me just take this, f2. Let's try to find the truth table for it. First of all, look at how many variables you have. 2, x and y. All right. So let me create a column like this, x and y, and my output is f2. Let's do it together, at least for one. I know you might already know this, obviously, but just for once. There are 4 possible combinations with 2 variables, 0, 0, 0, 1, 1, 0, 1, 1. I'm going to put all 4 of them. And I'm going to just plug in these numbers one after the other in this function and see how it looks like. Okay? So let's do it together. Let's put in the first combination, 0, 0. So x would be 0, y would be 0, 0 plus 0 times, basically this is AND, x again, so x is 0. So let's do one step at a time. 0 plus 0, these are basically 2 inputs in an OR combination. Do you remember when does OR give a 0 output? Only when both inputs are 0. Isn't that the case here? You're taking OR of 2 zeros. So essentially, you are going to get 0 here and then an AND of 0. And it's like both 0, obviously 0. Okay, so this combination is going to be 0. Let me take one more. Oh, didn't write it. All right. So let's get to the next one, which is 0, 1. So your x is 0, y is 1, and then x is 0 again. Now what? 0 plus 1, which is, sorry, it's for some reason moved. 0 plus 1 should be 1. If you, don't remember, just look at the truth table for the OR. And this is 1 and 0. And this AND of, like any AND with 0 is basically going to get 0. AND is only going to give you 1 when both of the operands are 1, which is not here, right? So you're going to get 0 again. Let's move to the third row. And I'm going to do it once. Don't worry. I'm not going to go through all these cases. All right, 1, 0. So x is 1, y is 0, but x is also 1 here. So now 1 plus 0 should give you what? Quickly. 1 and then 1 should be 1. So now we have finally gotten 1 as an output. Last but not least, the last row, 1 plus 1. Yes. Thank you. So 1 plus 1 times 1 is basically 1, as you can see. All right. So that's how you painstakingly create truth table. You can painstakingly create truth tables this way, right? It could be a more complicated function, right? More complicated with more variables. But this is the process. This is the practical process. All right. Okay. It can be difficult to do manually, but you can always use a computer program to just back calculate, right? Okay. But we don't have to do it nowadays, as you can imagine. All right. Before moving to the next section, I want to highlight this slide. It's not letting me clear of this marking, so I'm gonna discard these changes again and then put it back. All right. What you're looking at is the first row is AND and NAND. Let's take a closer look at the comparison between AND and NAND, right? So just take a look at the output for the AND truth table. And for the same combination, you have the exact opposite output. Flipped. Wherever you have 0, you have 1. So NAND is nothing but an invert of the AND. Similarly, OR and NOR, wherever you have 1, for NOR you have 0. So basically flipped. Now, I want to highlight a special gate here. It's called an XOR gate. Okay? It's Boolean function, Boolean representation. I'm going to write it here. Imagine you have two inputs, A and B. It should be AB bar plus A bar B. That's how it is represented in Boolean function form. Okay, but you don't have to, I mean, you could put in 0 and 1 and test how it looks like. But I can also represent it logic using real life logic like this. All right. 1 second, sorry. Okay, now it's working. So we could also use a real life concept. Notice you have 0 as output when both inputs match. So when both of them are 0 or both of them are 1, your output is 0. And when you have a mismatch, notice when you have a mismatch between the two inputs, your output becomes 1. All right. So XOR, also known as exclusive OR, is a unique logic that tests whether two inputs match with each other. Are we all good? I can always represent that using the function, like I said, AB bar plus A bar B. That is the XOR of A and B. Okay. But it's a very comparatively simple truth table to remember. And obviously, as the name suggests, XNOR will be just the not of XOR, like exactly the opposite. So notice wherever you have 1, 1 here for XOR, you have 0, 0, and there are others. So XNOR will show you 1 exactly when both inputs are matched. Okay, now, can anybody see a use case for specifically this logic gate? Can anybody? This is not a fundamental, this is not a building block logic gate, as you can see. I didn't tell you that with XOR you can make any logic. That would be NAND and NOR. It's not special because of that reason. But there is a special function that this particular logic gate serves, especially in the age of AI. Okay, that's why super simple concept. Things are not too difficult, honestly. Can anybody guess if, as an engineer, right? How do you engineers are supposed to make useful stuff out of fundamental knowledge, right? Oh, you use gravity theory to make rockets, for example, right? You don't just deal with theory. So what would you do if I give you this, if I had given you this picture in a logic gate, that it gives you 0 as output when things match? Can anybody? Comparing two things together, that's the first thing I would do. Thank you. Right? Don't you think? So it's a logical function that you don't have to manually see whether these things match. Beat what? Like just take a photo of your face. I hope you can see where I'm going with it. Just take a photo of your face, represent that in binary, and then maybe compare that with another photo, bit by bit, and see whether the XORs are, if you get like 90% match, that's you. If you get like 10% match, probably not you. Does that make sense, folks? So this is a very simple approach, a brute force approach towards recognition, image recognition. Not just image recognition, in data centers, in today's data centers, imagine you use Google Drive or OneDrive, right? And you upload your valuable files there, hoping for a safe storage. If for some reason you hear that, hey, Google server crashed and your files are gone, you can go and sue them. If you take a paid subscription, for example, right? You're paying say $5 per month, but then when their server crashes, you can sue them for like, hey, you basically $1 million, I don't know, right? So they have to make sure that they have backups of backups of backups. And they basically just keep creating backups of their servers. Not only for they have their own files as well. They have to keep backups of that. What if there is a cyber attack, right? And all their hard work will be gone then. So when a server creates a copy, it performs a bitwise XOR for all of them. This is called basically integrity checking, whether your copy was successful. Do you remember I had a slide in the very first lecture where there was cat and bat, and I showed you there is 1 bit mismatch between cat and bat, right? Just 1 bit. That's exactly the case. You have to pay attention to every bit. And imagine for XOR of A and B, A can be a bit coming from the original file, 1 bit of the original file. B will be that corresponding bit for the copied file. Are you still with me? So A coming from the original file, B from the copied file, and you're XORing them. And if they match, you're good. If they don't match, if you have a flag like what you have in XOR, whenever there is a mismatch, it gives you 1. That means there will be a flag raised. That means something went wrong. And you know exactly which position is not matching. So you can go back and repeat it, right? This is another example. And there are other use cases in cryptography and cybersecurity, which I'm not going here in too much detail. All right, so you see there is direct use case there. All right. That's why these gates are very, very uniquely suited to assess equality versus difference. Do you have two things equal or same, or are they different? All right, moving to the last slide of this lecture, and then we'll start with the next one today. This is basically a look ahead of what's coming in front of us. We'll be using VHDL, which is a hardware description language. I told you that we don't manually design things anymore, right? We use software, obviously, because things are getting complicated and you cannot manually like hand sketch stuff anymore. You need to understand the fundamental concepts, because otherwise, how will you code, right? But then after that, you code. You basically just code and scale it up from 10 to 100 to million to billion easily. So there are many hardware description languages, but there are two that are kind of universally used, and VHDL is one of them, right? And these are also used in industry. We'll introduce you to VHDL in this course. You'll be using them for some of your labs, so don't worry. I just want to show you that how do you represent different logic operations in VHDL code. Just want to show you how simple it is, and because the engineers made it simple, okay? So this is your output. This is one input, this is another input. You want to do an AND of A and B, you basically spell it out. All right, A and B. So this is implementing an AND operation. Next one is implementing an OR operation. Next one is implementing a NOT operation, and so on. As simple as that. Okay, and don't worry, we'll basically do real coding. So this is just a look ahead of what's coming. You can also do XOR and other logic gates as well. There is a list. Okay, and you use this assign operator instead of equal. So basically you assign A and B to this function, this output Y. Simple. Okay. All right, so let's conclude this lecture and move to the next one. Where we'll take a deeper dive into binary arithmetic, and we'll take a look at some additional concepts about Boolean operators. Most of this will be, I hope, very simple and to some degree repetitive for some people. But trust me, I only cherry pick the concepts that are absolutely critical and necessary for us to make sure we understand. We are all on the same page. I understand that out of the 90 of you, maybe 70 will probably already remember this, but I'm also shooting for the other 20. I don't want to, because this is a very critical foundational course, and we're going to go through some completely new concepts that are coming up, right? I don't want to put you in a position that, hey, simply because you couldn't review this well, you don't understand the next steps, right? And if it is already clear to you, that's great. By all means, just wait on a few classes, and hopefully we'll be there where everybody is new with everything. Okay. And there are other reasons why maybe you know how to add binary numbers. I'm not here to teach you how to add binary numbers. You have calculators, you have ChatGPT for it. I'm here to show you, basically help you see it in a different way. Don't just see it as an exercise that you have to do because you were assigned a homework. Because these are used in making hardware design decisions. We basically look at how do we add, and then we design an adder hardware to mimic that operation in actual practical physical form. A calculator, you are user of a calculator, but you are not making a calculator yet. But you are trying to learn how it is made, essentially, right? All right, anyways. So binary addition is basically like decimal addition that we all learned as kids. And except for the fact it is kind of simpler, it just gets a little bit confusing for one case, as you remember. When you add 1 and 1, what do you get? Anybody remembers? Can you tell me quickly? 1 0, right? 1 0. It's not obviously 10, it's 1 0. So you have 0 in the same bit and 1 as carry. That's how we represent it. Now, as I told you, I will help you look at the same concept in a different way. Imagine you have a certain bit system in your hardware, like you have 8-bit system. Okay. You add two numbers, two binary numbers, both are 8 bits, 8, 8. And then you generate a carry which gets to the 9th bit. Notice that the carry can take more number of, can require more number of bits than you allocate it. Does that make sense? So when you design hardware, you have to make sure that you are aware of how much carry your operations can generate. And that's how you design your memory size. You might be wondering, okay, one here and there, how does that create a difference? Let me show you. Basically, we have two slides dedicated for how 1-bit reduction can lead to drastic changes in the capability of your hardware. All right, let me not fast forward yet, but trust me, it's going to be there, and I'm going to connect back to this concept that I just told you. That this fact that binary addition can generate carry, and that carry can take more bits than your original input bits. So your inputs were both 1-bit numbers, but your sum requires 2 bits now. Output, sum, and carry, right? So this simple concept will have to be accounted for in hardware design. Okay, now, do I need to go through this addition, or are you guys okay with it? Super simple demonstration of when you add two numbers, you put the sum here, you take the carry, and so on. And apparently you end up with a carry that takes 1 bit more than the original number of bits you had in your numbers. Okay, moving forward to the multiplication of, why not subtraction? I'll tell you in a second. That comes last. Multiplication. I think my personal opinion is multiplication is super simpler for binary, even simpler than what we have in decimal, because all you have to do is just multiply zeros and ones. And this is super simple. Okay? And if you notice, this is essentially an AND operation. You see that? Multiplication is nothing but an AND operation. So if you create an AND gate in Boolean platform, you can use that AND gate to do multiplication. Simple. All right. Now, just a quick recap of how to do it. As an example, if you want to just quickly recap, you just multiply like you do in decimal. You shift 1 bit at a time, and then you basically add them up together. So a multiplication requires an AND operation and an adder. So when I teach, fast forward to 433, Introduction to VLSI, I teach the design of adder circuits, and we use something called ripple carry adder. And apparently, when you design a multiplier, you can reuse your adders that you designed. But you also need a bunch of AND gates because, multiplication operation, as you see here, is not, just compare the truth table. 0, 0 gives you 0. Everything gives you 0 except for when you have both input as 1. So it's an AND operation. So you need an AND gate and an adder circuit to do that. And surprise, surprise, I didn't tell you this. Adder, when you try to add two numbers, A and B, the sum of these two numbers is the XOR of these two bits. Isn't that interesting? I just told you. All right. So you can use an XOR gate to add things as well. So you just design an XOR gate and an AND gate and connect them in a certain way. You get a multiplication feature as well. All right. Let me move to the next one. I just wanted to show you a concept that sometimes, and this basically relates to the carry problem that I told you. Notice that when you multiply, you create a long chain, depending on how many numbers are there. You create a long chain. Imagine a situation where all of these are 1. So you'll keep adding them up, and you'll have more than 1 bit of carry. Your carry could be 101, for example. Do you see where I'm going with it? Probably not. Let me show you one direct example here. Let's focus on this one. So just for a second, consider this is 1, 1, 1, 1. So I'm adding 4 ones here. When you add 2 of them, you get 1, 0. When you add 3 of them, you get 1, 1. When you add 4 of them, what do you get? 1, 0, 0. Does that make sense? But you can only have one of those bits here, which is the last one, 0. But what do you carry? You carry 2 bits. So you're not overflowing by just a bit, you're overflowing by 2 bits. And this could be even worse if you have even more, rows coming down, right? And who determines how many rows will be there? The size of your numbers. You can have 8 bits, so 8 rows. You see the problem here? So to avoid such, problem with overflowing carry, oftentimes in hardware design, we just add 2 at a time. So for example, we just 2 at a time and just take the output, add the next one with it. So we just take 2, these are called partial products, 2 partial products at a time and add them instead of adding all of them simultaneously with an adder. This is a hardware decision. I know it might sound a little bit confusing because I'm getting ahead of myself. Just wanted to point you towards a hardware decision that we have to make based on how the math is done. This is how the math is done. You have to add them together. But when I try to add them, I have to manage carry, which can overflow. Okay, I will keep some extra bits for it. I will keep like 4 bits extra. But I'll show you, hopefully by the end of this class, you'll be able to see how a single bit can drastically change your hardware capability. So I don't want to do that. I don't want to just keep 4 extra bits. Even 1 extra bit is too much. Okay, so I'll show you that. All right, finally, binary division is exactly as the decimal division. But let me get back to this after we complete the subtraction. Okay, I want to show you how division works essentially. But apparently, it is a unique hardware that allows us to do binary division specifically for binary numbers. Okay, I want to show you this slide before we conclude today's lecture because this is important, and hopefully this will show you what I mean. I've been like pointing to 1 bit is so important, blah blah blah, right? So notice I haven't showed you the slide for subtraction. Why is that? Because representing negative numbers in binary has been a challenge. Okay, so apparently a minus b is same as adding a with negative b, as you can see. In binary operation, we typically just add 2 numbers. We don't have to create a circuit or hardware for subtraction. It's all for addition. We just have to represent the number as a negative number and then add it with whatever we have. Okay, so there have been a few approaches that people tried, and I'm going to show you how these things work. Okay, we are going to take a 4-bit number system, 4 bits, just for simplicity. We have 4 bits. Okay, with 4 digits, you could represent up to. Can anybody tell me how many combinations you can get out of 4 digits? How many can I do? 16. Yes, right? But here is why I'm going to left with just 8. Because I'm going to use one of these bits, right? Just the most significant one to only represent positive or negative. So if it is 0, it will represent a positive number. If it is 1, it will represent a negative number. So I'm not going to use it for any other purpose. So I'm left with 3 digits only. Okay. So that's why with 3 digits, you can have 8 combinations. That's why there are 8 rows. Notice all of these are positive integers and they have 0 in their sign bit, and the remainder are just the regular numbers. And in this column, the leftmost, the most significant bit is 1, and others are just a standard binary numbers for 0 to 7. Are we all good so far? It sounds super simple to represent. You represent the leftmost bit as the sign bit, and the others are used to represent the numbers. And you have a way to represent positive number and negative number. Super simple convention. Are you all good so far with it? Okay. There is a challenge. The challenge is when you okay, the challenge is this. As I just told you, if you have a minus b, you should be able to represent that as a plus negative b. But when you represent binary numbers as positive and negative using this approach that I told you, this approach has a name. It's called sign and magnitude approach. You use a sign bit and the remainder is for magnitude. So that's a sign and magnitude approach. But when you have 2 numbers represented using sign and magnitude approach, when you try to add them, which is supposed to represent subtraction, the numbers don't add up. You don't get the real subtraction result. You can represent, you can tell the computer to treat it so, but when you try to do an operation, when you add these two, they don't represent subtraction actually. So you get a number that doesn't make any sense. Am I making any sense at all? Okay, so try adding this number with the other one, and you'll see the output that you get doesn't really represent the subtraction result that should be. For that, what you have to do is, first of all, the first step is taking 1's complement, and the second step is to take 2's complement. Still with me? I'm not going to go through the mathematical arguments here. I'm going to just show you what to do first. So this is your sign and magnitude number. For 1's complement, you basically just invert the digits. So wherever you have 0, you make them 1. Wherever you have 1, you make them 0. Take a look at this. 000, you have 111. 001, you make it 110. So you just flip the digits. Do you see that, folks? 011, you make 100. So you take the 1's complement of the numbers that you are trying to represent. And then 2's complement is basically 1's complement plus 1. Okay. There is another easier way to calculate it. If you just try to calculate manually quickly, I mean, you don't have to do it manually. That would be just take a look at a number. Say, let's take a row, this one. Take a look at a number, and I'll also take this one. Okay, take a look at a number until you hit the first one. So apparently for this number, the first one appears in the first position. Are you still with me or no? I think this is easier to see. Let me show you, because I don't want it to hit at the first point. So here, this is where your first one hits. So this is your first one. And then you basically just flip the number. What I mean by that, let me just go here. Let's start. A second. Okay, so 110110. Say this is the number, or one more 0. If I ask you to take 1's complement, just flip the digits. 0010011. Super simple as it gets. 2's complement, Practically, you should just do it and just go through the math. But there is a shortcut that people do. That is, imagine if you have a number like this. Say this is the number. Start with the first one that you get from the right hand side. This one. So 0, 0, 1. And then flip the remaining bits, like 0, 1, 0, 0, something like that. Yeah, that's the shortcut that people use, and it's also mentioned in the textbook. You'll see. So thankfully, you don't have to do any of this manually ever, but you have to know this is what is done. You know why? Okay, if I ask you to make a circuit quickly, have 3 minutes. If I ask you to make a circuit, and every once in a while, especially the initial phase of this course, I take these tangents, and trust me, these are worth it. Hopefully, it will help you see why am I teaching you something that you will never have to do manually. You'll never have to do one's complement manually ever in your life, I think. But why am I telling you how to do it? Can anybody tell me? This is another opportunity for extra credit. Not today. I'm giving you the opportunity to practice. Okay. Can anybody tell me a circuit that helps me make one's complement? Anybody? Is there a logic gate that I could use to do one's complement? I mean, you don't have to make it complicated. Yes. Yes. Inverter or not gate. Did I just tell you about it today? Right? It just flips the bits. So imagine you have a stream of binary bits. You take an inverter, which is a logic gate, the simplest possible gate ever. You might be wondering, why would I even, if somebody, why would somebody use inverter? Maybe because of this. You just take a number, you invert it, you get one's complement. And you add 1 to it, you get 2's complement and something like that. Okay. So long story short, I want to at least finish this before the class is over. After you take 2's complement, the way we subtract number is, this is the slide that you should see. A minus B is done this way. You take A and you take the 2's complement of B and you add them together. That's when you get the actual result. And to help you review this well, I will share a 5 minutes YouTube video, which, I mean, it's not like made by me, obviously. I'll share it on Canvas. Just listen to that 5-minute video and it will review the process. All right. So we'll stop here at the subtraction. We basically do an addition of 2's complement to subtract. Thank you.